Okay, so this is week 11. So the agenda we're going to do is 2D and 3D Mohr circle. Some of you are taking manufacturing course that are doing with Mohr circle on carbon fiber. Okay, so you guys will know 2D already. But well, a lot of you have not taken my manufacturing course, especially the civil engineering. You don't take my manufacturing course, so I have to go through this again. Okay, so I'm going to talk about Mohr circle today. Okay, we're going to talk about Mohr circle today, both 2D and 3D, and then we're going to go for shear yield criteria, which is also known as Tresca criteria in 3D. Okay, so let's look at Mohr circle first. Okay, so in Mohr circle, you have normal stress and shear stress. Okay, so I'll teach how to use Mohr circle, how to relate the element to Mohr circle first. Okay, then I will teach you why is it important to use Mohr circle. Okay, so bear with me. Okay, so let's look at normal stress. So normal stress are stresses acting perpendicular to the surface. Okay, so any stresses that are acting perpendicular to the surface are known as normal stress, and a typical formula that we know will be stress is equal to force divided by area plus by my over I. Okay, so this is for axial loading. Okay, axial stress, and this is induced by bending moment. Okay, so now, so I'm going to show you, I'm going to draw two things now. Okay, I'm going to draw two things for you to see. So I want you to get used to seeing an element. Okay, so we're going to start drawing an element. Okay, so an element is basically square. Okay, so if we were to draw our transformation, okay, wrong direction. So we draw a transformation. So this will be always be our x, and that will be always be our y. Okay, so on an element, if you see arrow going this way, okay, so this is known as stress x, and this is known as stress y. Okay, so as we mentioned earlier, our stresses acting perpendicular to the surface, so the perpendicular is over here. Okay, so for this case, we are going to assume that stress x and stress y, they are both positive, and we're going to declare that stress x magnitude is greater than stress y. Just a condition that I've decided to impose. So some of you will ask me, Eugene, what is this element? Okay, what is this element? So an element, okay, I'm going to draw an element is basically you have a, for example, a cylindrical rod, right? And then this cylindrical rod, you know, is carrying some axial load. Okay, so this is my, for example, this is my px. If I would draw our transformation, this is x, y, and that would be our z. And then it's carrying some distributed load. Okay. right? Carrying some sort of distributed load, right? And then you have, for example, another example is you have a roller support on the bottom, right? You have a roller support. So where is this element? So an element is at any position, the region where, or the point where you're interested on the stress. Okay, so you decided to put an element down here. Okay, so I will call this element H. Okay, so element H, if we look at the plan view of element H, okay, so it's still not clear what is an element, right? So an element is a place of interest. So if we look at plan view, right, so this is Z and X, and this is element H. It's usually a set of strain gauge. Okay, so element H, you have a strain gauge going this way, strain gauge. So this is strain gauge 1. Okay, strain gauge 2. Okay, and then you have strain gauge number 3 at an angle. Okay. So it's basically your strain gauges. Okay, so basically are your strain gauges. So these strain gauges, what it does, right? It's able to what? The strain gauges are able. Okay, the strain gauge. Okay, are able to relate strain to stress by a change in resistance. Yes or no? Right? So the more your gauges are stretched, right? The more the gauges are stretched, the more the gauges are stretched or change in size, right? What will happen is the resistance will change. When the resistance change, okay, and the output is voltage change. So you measure the voltage, so you relate the voltage to your stresses. Okay, so they're all strain gauges. Okay, so that is what I mean by element. So it's able to relate strain to stress. Okay, right, by a change in resistance, and the output is voltage change. So that is what we mean by an element. Right. So coming where we are now, that is what we mean by an element. So we have an element, okay. Then we look at Mohr circle. Yeah, I want us to look at Mohr circle. So Mohr circle has 2 axes, right? So one axis on the x-axis, okay, is known as normal stress. Okay, x-axis. The thing is a bit confusing. Is that we thought of is usually we think x-axis will be stresses in the x direction. No, okay, x-axis means stress, normal stress, and then the vertical axis, right? The vertical axis is the shearing stress. And then we're going to assume, not assume, but we're going to specify that the shearing stress, I want you to know this, is clockwise shearing stress rotation. Bottom is anti-clockwise shearing stress rotation. So from what we have drawn, okay, from what we have just drawn, I'm going to stretch this out a bit. All right, so from what we have drawn so far, we know that stress X is greater than stress Y, okay, and both are positive. So this is my stress X line. Right over here, this is our stress X line. And then on the other side, or on over here, this is your stress y line, right? And I want us to have a habit. Once we see an element, right, we're going to call this at point x. Okay, there's our x, and then we're going to call here our point y. I want you, as I said, I want all of you to have a habit of doing that. Okay, I want you to have a habit of doing that. So once you start, anytime you start a problem like this, okay, I want you to have a habit to say that on the x on the plane intersecting the x-axis, okay, is your x, and then the plane intersecting your y-axis, that's your y. Okay, so over here where point x is, right, point x will be over here because it's on the stress x line, right? This is our stress x line, and the shear stress is equal to 0 for now. Okay, so you look at element, there's no shear stress. Then over here, right, this point will be your point y, right? And then we know from here, this is the center of circle. We usually call it O, right? And then from here, we draw a circle. You use your compass. By the way, your exam, you need a compass, okay? You draw a circle. Okay. So the center axis, this is the center axis, right? And I'm going to introduce you a term now. So the center axis over here, right, is what we call this distance from the 0 line to here, right? I repeat again, it's from the 0 line to here, right? So this is known as our stress average line. Okay, that is known as our stress average line, where the stress average is equal to stress x plus by stress y divided by 2. Okay, it's a very straightforward formula. You don't need even to memorize this. Okay, where stress average stress is equal to stress x plus by stress y divided by 2. So, but I want you to remember it's measured from 0. Okay, from 0. Okay, so this is how we relate normal stresses on Mohr circle. And I'll write something else down here, okay, which I did not, is your shear stress is equal to 0 down here. So we have no shear stress for this case. Okay, then I will draw another different configuration for you to see. Let you guys have time to copy. We have another element. Okay, so we have another element. So the element now, we have an arrow, okay, pointing downwards. So this stress y, and then over here, this will be our stress x. Okay, so for this case, we declare that stress x, so it's pointing away, is in tensile, positive, and stress y is negative, right? And then again, our shear is equal to 0. Okay, so we're going to again sketch out the Mohr circle, right? We're going to sketch. So we are going to draw our axis. So this is our normal stress. Then we have our shearing stress. I'll try to be the same like the one on top. So I want you to have the habit to draw the shearing stress is clockwise over here, down here is anti-clockwise. Right. So again, we start labeling that this is the plane intersecting the x-axis. This is the plane intersecting the y-axis. Okay. So now we know that from here, we know that stress x is positive. So we have it somewhere around here. Yeah, we have it somewhere around here. So that is your stress x line, right? and then your stress y is negative. So if this is 0, right, this is 0, negative means it's on the other side, right? So that is on the other side.